Yes, I welcome you all for another presentation on transistors configurations. And by the way, this is our lecture number 10, in which we are going to see the transistor configurations of bipolar junction transistor, right? So, if you recall our previous presentation, there we have seen so there are three types of configurations basically as far as the transistor is concerned. As the transistor has three terminals, so that is base, emitter and then collector. That's why a transistor can be operated into any one of three configurations, namely common base configuration, common emitter configuration and common collector configuration, right? So today in this presentation we will see the common base configuration, right? Let us see what is a common base configuration. It is okay, this is common base configuration. So I will explain you very briefly actually. Common base configuration, or in simple it can be called as CB configuration, you can say CB configuration, common base configuration, or simply you can call it as CB configurations also. So as I have already told you that in CB configuration the base terminal will be kept as common actually. If you see the physical representation, right? So this is the physical representation. This is your base terminal, this is your emitter terminal, this is your collector terminal. So now in this case, in this common base configuration, this base terminal is kept as common actually. This can be kept as common actually, means common is nothing but putting the terminal at zero potential, normally ground potential. So this particular can be represented like this. If you see here, normal in common base configuration, if you see, so this is something like this. So this is your NPN transistor normally. Let us say in this case the emitter terminal will be taken as, this is your collector terminal normally, this is your emitter terminal actually, this is your base terminal, this is your base terminal, this is what your transistor, right? This is what your transistor actually, this is the base terminal in general. This is what common is nothing but this is what the thing, this is the meaning of it actually. So this is the base terminal that is kept at zero potential, or can be put as the reference with respect to remaining two terminal. What is this? It is emitter actually, emitter. So this emitter terminal will be considered as input actually here. This is your input, whereas your collector will be taken as output normally, right? So this is your base terminal will be kept at zero potential normally, right? So now this is what your NPN transistor normally. Here if you see, remember that actually in common base configuration, so this is what your N actually, this is what NPN, let us say this is N, this is P, this is N, that's why it is called as NPN transistor. If it is PNP transistor, you can write like this, PNP, right? PNP or otherwise NPN, no problem. So here the very important point to remember is that now what is our main purpose of putting the transistor into common base configuration or common emitter configuration or common collector configuration? Why we should operate the transistor in this configuration? Because the main purpose of the transistor is to be act as, or the transistor shall be, that should act as an amplifier. So that is why we can connect the transistor into three configurations. Well, now so so as per this common base configuration, if you put in this case, now you can see that This is emitter and then base. So this is one junction actually. This is called input junction. This is the between emitter to base. This is called your input junction, or I can call it as J1 or input junction. And similarly, if you see the collector and then base, this is your normally your J2 or junction 2, you can call it as junction 2. Otherwise it is a output junction. This is input junction, you can call it as input junction, and this is what your output junction J2. J2 is our output junction. You can write here output junction, no problem. This is what your output junction. So this is J1 is your input junction. This is what your input junction, right? How now these junctions must be biased. How the voltages will be given between this input junction to the output junction. Remember that always. For a transistor which is to be operated as an amplifier, the input junction must be forward biased. Always remember, the input junction must be forward biased. Remember that, very very important. The input junction must be forward biased, whereas your output junction must be reverse biased. Standard point, very very important point to remember. This is reverse biased and input junction must be forward biased. Therefore, you must connect this input junction, means you must connect an external power supply or voltage between emitter to base terminal in such a way that your junction must be forward biased. Okay, so for that case, how the voltage, the power supply shall be connected here? It is N actually. N is nothing but, so it is NPN transistor basically. Therefore, in this case, and one more important point to note down here is that, so the first configuration is common base configuration and the second is the common emitter. In both these configuration, the output terminal must be the collector only. The collector terminal is taken as the output terminal. Remember that. In both common base as well as common emitter, in these two configurations, the output terminal, the output must be taken at collector itself. No confusion at all. Therefore, in common base, so base is kept at common, therefore collector must be taken at output. So this is the output terminal. Obviously, what is the remaining one? Emitter. Emitter itself is the input. I think some people may get confused in remembering all this. Nothing to confuse actually, very simple. So simple point, one point you should remember is that in common base and common emitter, these are the very important configurations. These two configurations only can be used for a transistor to be operated as an amplifier, whereas common collector will not be used actually. That common collector configuration will be used for some other application actually, for other purpose that CC configuration can be used. But as far as in amplifier, as far as the amplifier is concerned, only the CB configuration and the CE configuration, common base and common emitter configurations, will only be used as an amplifier. Common collector will not be used in an amplifier, but that can be used for some other purpose that I will explain you later. Therefore, you must focus on CB and CE only. Therefore, I am telling you that in both these cases, in both these CB as well as the next is the CE, in these two configurations, output must be taken at collector only, the standard point. Therefore, once the output is taken at collector, now again come to the CB. What is the CB means? Base shall be kept at common. Therefore, base you have to put at common like this, and collector is obviously your output. Then automatically what is the third terminal? That is emitter. Emitter must be input. Likewise, you have to remember very easily. Right, now coming to here again. Now how the external power supply voltages. So now it is the input junction. This is what your output junction. So the external power supplies shall be connected for these both the junctions. Therefore, how the power supply will be given here. So the input must be forward biased. So what is the forward bias? Is nothing but, so as in emitter is the input terminal, and here the your input terminal is nothing but N type. N type is nothing but, what are the majority carriers in N type? Electrons. Electrons are the negatively charged particle, therefore negative will be there. Therefore, in order to be forward biased, my voltage must be, how I should give? It is, you must give negative like this. So negative terminal must be like this your voltage connection. This is minus, this must be plus. Remember that. If you put, and obviously this can be, you can write it is nothing but your voltage between emitter to base only. You can write it as VEB. VEB only. So clear. This voltage is nothing but obviously between emitter to base terminal. Therefore, you can write like this V suffix EB. That is the voltage actually. Right. Therefore, if you connect this external power supply in this connection, therefore the minus terminal of the battery, if you connect to the emitter, it is a negative then here, because it is a n-type material. N-type is nothing but majority carriers or electrons. Electrons are the negatively charged, therefore negative will be there. Negative to negative, therefore it is a forward bias. Now if you give the connection of this VEB like this, then your input junction will be under forward biased. Coming to the output junction. So here again, if you see in output junction, so again here, that is nothing but you must see the collector n-type material. So here the collector is the n-type material. Again n-type is nothing but majority carriers are electrons only. Electrons are the negatively charged particle. Therefore for this you need to give the reverse biased. Therefore for reverse bias, what we should give? Opposite polarity. Means that, so it is something, it is negative actually. For this you must give positive, right? You must give positive. That's it. So this is positive and then this is the negative, right? Therefore this voltage is nothing but, this is the voltage between collector to base. Therefore it is voltage collector to base. You can write like this VCB. Clear? VCB. Is it not? This is what the thing basically. So here this is the direction of current actually. So this is the emitter current. It indicates the current. Therefore emitter current you can represent like this. Emitter current, the flow of current is like this actually. So if it is coming out, then obviously your base current flows like this. It is goes inward actually. This is IB, and your collector current also, the flow of current is like this. IC. This is the collector current. Therefore IB goes inside, IC comes like this, IE flows like this actually. This is the flow of current. Clear? I think you got this. Therefore this is what, if you give the external batteries connection like this, then it is the negative actually n-type material. So negative to the positive, therefore it is reverse biased. So now you can say it is a reverse biased. Therefore now if you connect the transistor like this, then this is called a common base configuration. This is a common base configuration circuit. Clear? In this case, we need to remember few points actually, as we have discussed in our previous presentation, that so for any amplifier circuit actually, okay, for any amplifier circuit, now it is a amplifier circuit in common base configuration. Now in this configuration, the transistor can be used as an amplifier, right? So there are four important parameters that we need to be considered, or we need to be focused. What are those parameters? You know, the parameters are, so between this input, at input junction, you must focus on what is its input impedance, that is R suffix I. Actually, that is what input impedance. What is the input impedance? And similarly at this output junction, you must observe that what is our output impedance, R naught, R suffix naught, R 0. This is R suffix I, nothing but I stands for input only, R input, or simply R suffix I. This is R output, R suffix output, or simply R naught. So this is input impedance, this is the output impedance. Then these are the two parameters. Other than these two, there are two more parameters. Those are nothing but the current gain. I will write here. The first is input impedance. What is that? Input impedance. Input. So input impedance is not, input impedance is normally it is a resistance only, input resistance. So in this terminology we will call it as input impedance, and normally it is denoted by R suffix I, R suffix I, small I. So normally input impedance is measured at the input junction only, remember that. So in this input junction, that impedance will be measured, right? That is input impedance, one parameter. The second parameter is output. What? Output impedance. Output impedance is nothing but simply again R naught suffix naught. So our output impedance is nothing but it is the output. Normally this impedance is measured at the output junction, at the output between collector to base here. This is the second parameter. What is the third parameter? Third parameter is the voltage gain. Third parameter is nothing but voltage gain. Voltage gain. Gain is represented by A, as it is voltage A suffix V. A suffix V is the voltage gain. Gain is denoted by capital A. It is for voltage, therefore A suffix V, voltage gain. And the fourth parameter is the current gain. What is the current gain? It is again A suffix I. These are the four parameters that we should remember and we should concentrate and we should focus on the transistor circuit while choosing that particular transistor as an amplifier. In general, in practice, normally for considering the transistor as an amplifier, then we must focus these four values. What is the input impedance of the transistor? What is the output impedance of that particular transistor? And what is its voltage gain? And what is its current gain? How those values are like that. Clear? So these are the things actually. So if you see mathematical also, RA, normally RA is nothing but that is measured at input side only. Input side only. So at this, what is RA actually? So what is Ohm's law? Actually Ohm's law states that V is equal to I into R. Clear? This is as per your Ohm's law, I into R. This implies from this what is R actually? R is equal to V by I. R is equal to V by I. So from this actually R is nothing but, so if you apply this rule here according to Ohm's law, R is equal to V by I. So here V is nothing but your input voltage only, that is VEB, emitter to base. And then what is the current? What is the input current? IE. IE is called input current. That is what the expression for R suffix I. This is what the expression for RA, input impedance. So to calculate the input impedance, you must take the ratio of VEB, input voltage by input current. This is your input voltage. This is external power supply normally, but you should consider the voltage actually emitter to base terminal. In between these two, what is the voltage is there? That voltage we have to consider, and what is the current flowing through this terminal, emitter terminal. Emitter terminal current is the input current. Therefore, input voltage by input current gives your input impedance. And similarly, what is your R naught? R naught is nothing but output actually. So in the same way, R naught is measured at the output voltage by output current. So output voltage is nothing but VCB. It is VCB by what is output current? IC. If you take that ratio, you will get your output impedance actually, R naught actually. Then what is the voltage gain? Voltage gain is nothing but output voltage by input voltage. What is the output voltage? Normally VCB. VCB by VEB. If you take that ratio VCB by VEB, that is what your voltage gain, third parameter. And what is the current gain actually? Current gain is nothing but output current by input current. What is output current? IC. IC is the output current. IA is the input current. Therefore, IC by IA. This we have seen in previous presentation actually. Clear? So, your current gain is nothing but A suffix I. This is nothing but output current, nothing but IC by IA. And this also denoted by the letter alpha actually. This we have seen in previous presentation, and alpha value is obviously it is less than 1 actually. So alpha value is less than 1, therefore the current gain value is less than 1 here. Remember that. So again, as far as our CB is concerned, I mean common base configuration is concerned, so normally the input is given here. This is the external power supply. In fact, this is actually DC analysis. If you consider the DC power supplies here, and if we study the character characteristics of the transistor, then this is called a normal DC analysis actually. So the same circuit can be used to study under AC analysis. So what is AC analysis? So AC analysis is nothing but the capacitive effect comes into the picture, because the capacitive effect will be, so the capacitance also will be taken into consideration for AC analysis, right? So if you remember from your diode concept, normally what is a PN diode? PN diode is nothing but, so it is a PN diode, nothing but it is a P-type material and an N-type material actually. Okay, so those are connected with an external battery power supply actually. Then with this, depending on the connection you will give here to this diode can be again same, will be operated in forward bias as well as the reverse bias, right? No problem. But internally, if you see internally during the forward bias, internally it is nothing but it is a P-type material. This P-type material will act as one plate and this N-type material will act as another plate. So means that what I mean to say is that two parallel plates differentiated by a small amount of distance, small gap will be there, I think, is it not? So that is called depletion width. I think we have seen this in previous presentation. That is called depletion width or depletion layer, you can say. The depletion width, some small amount of gap will be there, right? That is the width actually. In between these two materials, you will have certain gap, that is the depletion width actually. Thereby, so for these two plates, we are giving some external voltage. So means that what? So these two plates will act as a parallel plates. Parallel plates. This is one plate, this is another plate. P-type material, N-type material. These two plates are connected with a external power supply. Then this is called as the capacitive effect. It is a parallel plate capacitor. So PN diode, okay, works as a parallel plate capacitor. What is a capacitive effect? What is a capacitive effect? That I will explain you just little bit for your information. What is a capacitive effect? Capacitive effect is nothing but actually whenever two parallel plates are separated by a small amount of distance, and okay, so let us say this is one plate normally, this is one plate, this is another plate, plate 1 and plate 2, clear? So these are connected with some external battery, some voltage I will give, plus and then minus, some electric field or voltage, otherwise no problem. So the distance is small distance actually, small gap will be there. So this is plate 1, this is plate 1 and this is plate 2 actually. This is external voltage, electric field, or you can say some voltage. You can say some voltage, external voltage. So remember that. So this voltage, you can vary this voltage. It is a variable, no problem. It is a variable voltage. Show the arrow mark here. Therefore, it is a variable voltage. So means that what you know. So this is the plus terminal of the battery is connected to the plate 1 and the negative terminal of the battery is connected to the plate 2. Clear? So as you connect the power supply like this, because of this positive, you may give some 10 volts or whatever the volts you need to give, no problem. Whatever the voltage you want to give, you can give, no problem. So because of this plus terminal here for this plate, on this plate, positive charges will be deposited. You know, positive charges will be deposited here. Because of the plus terminal, positive charges will be deposited. Because of this negative symbol, means negative charges will be deposited here. Negative charges. Both are the charges only. This is simply positive charge. This is the negative charge only, but the charge is represented by the letter Q. Na? The charge is denoted by the letter Q. Q is the representation of charge. Therefore, now this is voltage actually. In general, I can represent the voltage as V actually. Now, as you go on increase or decrease, whatever the way, okay, if you increase, if you do some incremental change, that is nothing but dV, let us say dV nothing but decremental or incremental change in voltage, then there is a corresponding change in dQ also, means, so for dV you will have dQ, So at positive side as well as the negative side, but collectively I consider it as a commonly I will take dq only. Commonly I will consider dq only. Okay, maybe positive or negative, no problem, but collectively I can consider a single parameter as dq only. Means that what? For change in dv, you will get change in charge also. For change in voltage, you will get change in charge. That is called dv proportional to dq. dv, if you do some small change in the voltage, then you will have the same amount of change in the charge also. Therefore, now if you take the ratio dq by dv, if you take the ratio dq by dv, this ratio is called as the capacitive effect. This is what capacitance actually. That is the actual definition of a capacitance. This is how you define the definition of a capacitance. Otherwise, normally, if you ask what is the capacitance, normally you will say something Q by V, no? Have you remembered this? C is equal to Q by V. How you derived? This is the proof. This is the proof actually for Q by V. This is the nothing. Okay, it is from parallel definition of a parallel plate only. Parallel plate differentiated small distance, negligible distance, and if you connect some external voltage like that, then you will have this capacitive effect dq by dv. This ratio is called as capacitance, right? Therefore, what I mean to say is that internally in the diode, you will have capacitance. And during the DC analysis, the capacitance will not be considered. Remember that. During DC analysis, the capacitance will not be considered. But when you consider that particular diode or transistor, whatever is under AC analysis, capacitance must be considered, because a capacitance is an AC element. Sometimes you can be use the same into DC analysis also, depending on the requirement and the application, right? It is a capacitive, it is a AC element basically. AC element, capacitance is a AC element, right? Therefore, this is the basic definition of a capacitance. So, if you consider the PN diode, say for example, if it is connected under forward bias condition, so you will get one type of capacitance. Have you remembered it? What is the capacitance during under the forward bias? Remember that? So, during the forward bias of a PN diode, you will have the capacitance C suffix D. It is called diffusion capacitance. It is called diffusion capacitance. It is nothing but, I will explain you, I will write the definition here. So, if you connect the diode under forward bias condition, you will have one type of capacitance, that is CD, called diffusion capacitance. What is the expression you know? Tau times I by eta times V into T. This is very important formula even for the gate examination point of view. Diffusion capacitance, C suffix D is called as diffusion. Here D stands for diffusion. It is a diffusion capacitance, right? Diffusion capacitance, also called as storage capacitance. This is also called as storage. It is also called as storage capacitance, right? Storage capacitance, C suffix D. Tau is some constant, right? I is the diode current, eta is constant of the material, maybe germanium and then silicon. It varies for both of the materials depending on the material. And Vt is the volt equivalent temperature. Vt is the volt equivalent. You know what is Vt? Vt is equal to, it is 26 millivolts actually. 26 is millivolts at room temperature. Vt is equal to 26 millivolts at room temperature. There is a formula. I think you have remembered that, Einstein's relationship. What is the Einstein's relationship? This is the formula basically. Diffusion capacitance, remember that. This is the capacitance of the diode during forward bias condition. And again, if you connect that same diode into reverse bias condition, again in the reverse bias you will have another type of capacitance. What is that capacitance? Under reverse bias condition, that is nothing but C suffix T. C suffix T, that is called transition capacitance. C suffix T is called as transition capacitance. And again, There is a small mathematical expression for that. Okay, what is the expression that? Epsilon A by double V. Epsilon A by W. Epsilon is the permittivity of the area. A is the cross-sectional area of that junction depletion layer, and W is the width of the depletion layer. This is the cross-sectional area. This is the width of the depletion layer, cross-sectional of the depletion layer, and epsilon is the permittivity of that material, of that medium. Clear? This is the transition capacitance, also called as space charge capacitance, also called as space charge, also called as depletion capacitance, transition capacitance or space charge capacitance, or otherwise also called as depletion capacitance. So this is the expression for transition capacitance. So these are the two types of capacitance normally you will have in PN diode during forward bias as well as the reverse bias, right? And one more important thing here to remember is that so whenever you connect the diode under forward bias condition, normally in general internally in the PN diode both of the capacitance will exist in general. In general both these capacitance will internally exist, but in forward bias condition the diffusion capacitance will be dominant than transition capacitance. Means the value of CD, diffusion capacitance, is more than your transition capacitance during forward bias. Whereas coming to the reverse bias, under reverse bias condition the transition capacitance is dominant than the CD. Means that what you know, so the transition capacitance value is more than the diffusion capacitance in the reverse bias condition. Why I am explaining all this, the same concept will come in the transistor also, because in the previous presentation, in earlier presentation, I have already told you that it is PNP is nothing but it is so internally it has two PN diodes actually. Internally it is a NPN, therefore NP, nothing but it is a PN diode. Again here PN, another PN diode, therefore is one PN diode, another PN diode. That is why as the individual PN diode has the capacitances internally, so as we are using the same concept here, here also you will have capacitance you will have, and they will be considered during your AC analysis of the transistor. However, during this is called DC analysis actually. If you apply the DC power supplies, then this is called a DC circuit, DC power supply circuit. So during DC, AC elements will not be considered, not required, because DC needs no AC. Clear? Not required. Therefore, this is the basic circuit diagram. Therefore, remember that the four parameters need to be considered: input impedance, output impedance, voltage gain, and then current gain. And also one more important point here itself I am mentioning that also for the transistor to be selected as an amplifier, then we must see that all these four parameters must be very moderate. Any one should not be less. All four parameters must be moderate. They must be sufficiently enough, right? So in that case only you will get a perfect amplification of the input signal. It will be amplified properly and you will get the proper output. Otherwise, if any one of the parameter becomes very less, then obviously you will get a poor amplification actually. You will not get the proper amplification. Say for example, it is a poor amplifier actually. The CB itself is a poor amplifier. Tell me why? Tell me why? What is the reason? Definitely it is very easy. Nothing difficult to explain here, because so you must remember these four: input impedance, output impedance, voltage gain, and then current gain. So if you remember, what is the current gain actually? It is output current by input current. Means that your IC by IA, nothing but your alpha. What is the alpha value? It is less than 1. Therefore less than 1. So therefore that is why it is a poor. The value of your current gain is a poor actually. That's why one parameter is already gone. Therefore that is the reason why most of the times CB will not be used most of the time as an amplifier. CB circuit is very rarely used, or you can say it is almost all it will not be used actually. the common emitter configuration is widely popularly used configuration. Not only that current gain is less here, even the input impedance is also very less for common base configuration. If you calculate the input impedance based on this formula, you will get very less value normally. The input impedance is maybe in the order of ohms only. It is about some 50 ohms, like that you will get normally 50 ohms input impedance. Output impedance is somehow okay, but voltage gain is also somehow okay, but these two, input impedance and current gain, these two values are very less values actually. These are very less value. That's why CB configuration most of the time we will not consider actually. CB configuration will not be considered, right? That is the reason we will discard this configuration actually. But and therefore that's why we will go for the next configuration, that is the common emitter configuration. If you see in common emitter configuration, so the input impedance, the output impedance, the current gain and voltage gain, all four parameters you will get moderate values actually. That I will explain you in the next presentation. I think this is quite enough in for this today's presentation. I hope you understood well, and right. So I finish off this presentation here, and we will continue the extension of this into the next presentation, right? So definitely don't forget to give your valuable comments and suggestions, and your observations. That definitely will helps me to improve and to relook, and so that it will be very useful for most of the students to uh, to get the basic information about the subject, to get the more information, right? So definitely try to pass this information, or to send or to forward these information to as many as you can. Finally, what I wish to is that definitely every student should know the basic concepts of the subject, thereby you all should excel in your careers, right? With this, I finish off today's presentation. We'll meet in the next. Okay, until that, have a nice day.